Hey everyone, I'm JVacek and today we'll be talking about KI5 and more specifically signal receiving. Relevant courses I'm in ECE 332, ECE 312, and ECE 342. So what goes into receiving a signal? So in KI4 we talked about sending signals, but today we're going to talk about receiving signals. So kind of the chain of events that occurs when receiving a signal. We have our antenna, which senses the signal. We have a diplexer. A diplexer essentially just switches between whether we're going to receive or send the signal. We have our bandpass filter. We have our low noise amplifier and mixer. We have another amp. Then we have our low pass filter. And finally, after the low pass filter, it goes through some more additional signal processing, which we will not cover. So let's just start with the antenna and the diplexer. So basically, if we assume maybe a dipole antenna, the antenna needs to be aligned with the direction of the electric field, so it can sense changes in potential and therefore induce a current. So the antenna needs to be aligned with the direction of the magnetic field, or the electric field, excuse me. Secondly, we can think of this more from a circuit point of view. We need to use a matching network to achieve max power transfer. So when we do circuit analysis, typically when we want to find Thevenin impedance and we want to attach a load impedance, the Thevenin impedance and the load impedance need to be matched. More specifically, they actually need to be complex conjugates of each other to achieve max power transfer. So the matching network actually makes sure that the RF circuitry that does more signal processing and the antenna are actually matched. And so we also need to have, it's kind of just fundamental, that frequency and the length of an antenna are inversely proportional. So if you have a very low frequency, you need a very long antenna. And if you have a very high frequency, you need a very low antenna or a very short antenna. And we also use this thing called electrical length. And we can, instead of just stretching out a very long antenna, maybe like of 1 meter for a certain frequency, we can design it in such a way that if you did stretch it out, it would be 1 meter long, but we can compact it into something that's like a square inch or something because we've designed it in such a way. Now, like I said earlier, a diplexer just switches between whether we're going to send a signal or receive a signal. So let's look at a bandpass filter and a low noise amplifier. So there's two purposes of a bandpass filter and a low noise amplifier. First is when we receive a signal, it's not just our signal. So for example, if the signal we're trying to receive is at 300 megahertz, we're going to have additional signals, maybe at 500 megahertz, 200 megahertz, and the bandpass filter essentially just gets rid of all the other signals, so we only have our 300 megahertz signal that we're trying to receive. Secondly, Mother Nature, we can't avoid it, adds noise to our signal. And noise is something we cannot control, but the bandpass filter, once again, helps filter out unwanted noise. So here's just kind of a typical bandpass filter. One way we can create it is we attach a low pass filter and a high pass filter in series. And what we do this circuit-wise is we can actually create a amplifier, so our low noise amplifier and a bandpass filter in essentially the same way. So a bandpass filter, like the gain of any amplifier is GM R out. And if you have a parallel connection of an LC circuit, its resonant frequency is at F naught. And what that actually mean is that at F naught, the impedance of this circuit is at its max. So we can create a bandpass filter by centering our bandpass filter at frequency F naught. So that's what we're actually doing here. We amplify the signal by centering our frequency at F naught, and we also create a bandpass filter based on how the general shape of how the impedance looks like for an LC in parallel circuit. So now let's go to the mixer and amplifier. So when we actually, seems counterintuitive that once we send a signal, we also mix it, but when we receive a signal, we also mix it again. So for example, let's look at this from a 312 point of view. If we have a signal that we received at omega naught, maybe 300 megahertz, we mix it again with another signal omega naught at 300 megahertz. So here's the signal we received, the spectrum of it, 2 copies, one at omega naught, the other at minus omega naught, and we mix it again. That once again creates 2 more copies. We shift one over omega naught and we shift one the other way at omega naught. So we create a center copy at 0, another copy at 2 omega naught, and a final copy at minus 2 omega naught. So what that does is, if this is our original signal, or this is maybe our signal we're trying to receive, our voice signal, x of t, or x of j omega, excuse me, we have 2 copies at omega naught, but once we mix it again, we have our original copy centered at 0 with a bandwidth of omega b, for example, and now we have our original copy, x of j omega, and what we need to do is we need to send x of j omega through another amplifier. It could be a differential amplifier, anything. It's something that doesn't add any additional noise necessarily, or not too much. And because when we actually mix signals, we lower the magnitude of the transfer function of them. So lastly, we have our low pass filter. And what this low pass filter does is, like I said, with our mixer, we've mixed the signal, we've gone through, and now we send it through a low pass. And what the low pass filter does is it gets rid of those 2 copies at 2 omega naught and minus 2 omega naught. So we're left with our original copy of x of j omega, or our voice signal that we sent over the air. So here's maybe a typical low pass filter. A low pass filter has, for this one, it has 60 dB gain. So maybe we've amplified the signal to bring it back to its normal value. And it has a cutoff frequency at 10 radians per second. And an interesting thing kind of in technology today, we actually have programmable gain arrays, where if like I'm a really loud speaker, the receiving antenna recognizes it and it kind of lowers the gain so I don't come out on the other end of the signal as a very loud person or ridiculously loud. But if I'm also a really soft speaking person, I actually get the gain on this programmable gain amplifier actually increases even more. So that's about it. That's kind of how we receive signals in a typical cell phone. Thank you very much.